So, welcome back to this class on hardware security. So, we shall be continuing our discussion on differential fault attacks on AES. So, in particular, we shall be trying to look into how to perform DFA attack on AES with one single fault. So, in the last class we saw that with two faults, right, two single byte faults, we were able to reduce the AES key size to a unique value. But now suppose and we have seen that if there is one single fault, then you reduce the AES key size to 2 power of 32 values. So, the question now that we will try to take up is that with one single fault, can you reduce it further? Okay. And in particular, we will see that we can develop an algorithm through which you can do that, but you can reduce the key size to only 2 power of 8 values. But if you do that, then you need a time complexity of 2 power of 32, and then we will see a further improvement in which you can reduce the time complexity to 2 power of 30 values. That means on the average like 4 times faster. Okay. That means if in the previous case you were requiring like 60 minutes to do the attack, in this case you should require around 15 minutes to do the attack. It is significantly faster. So, the question is that can the attack work that we have seen with one single faulty cipher text? We have seen already that this is a summary, okay, and even then, right, with 2 power of 32 probably a brute force search is still possible, but we would try to reduce it further. Okay. So, here is again some comparisons of existing fault attacks. For example, there was an old work by Blomart which requires around 128 faults, okay, and then there was like 2 works from Girard which requires around 50 and 250 faults. So, the whole pursuit, right, has been again there was a paper by Duzat which requires around 40 faults, and then by Piret which requires around 2 faults, and then there was an attack that we reduced the time complexity to 2 power of 32 values, but still requires around 2 faults. Okay. So, therefore, the pursuit has been to reduce the number of faults, and we would like to continue this trend and reduce it further. Okay. So, here are some more attacks that were tried by some other groups, and what we are still trying to reduce is we are still trying to optimize the fault attack. So, therefore, this is the current status right now, where you see that the AES key size can be reduced from 2 power of 32 to 2 power of 8 values only for a single byte fault. And this essentially makes the attack very practical, because that means you just need one single shot to reduce the key size to only 256 guesses, which is essentially very easy. And so, these are the 2 references that I will be using and elaborating in this work. So, what are the drawbacks of the existing DFA? So, basically it requires a brute force search of 2 power of 32 values, and it has got a time complexity of 2 power of 32. So, we would like to reduce this space complexity. If I say that the brute force search of 2 power of 32, we would also try to reduce the time complexity further. So, therefore, we will try to improve both on the search complexity as well as the time complexity of the attack. So, how can we reduce the search space of attack? In the first space, we have seen that we have basically we find the 2 power of 32 candidates of the 10th round key, but in the second phase, we shall deduce 4 further differential equations which we had neglected in the previous attack. Okay. So, if you remember that the propagation, there was in the 9th round there was also certain equations among the faults which we did not exploit in the attack. We were just considered about the final equation sets which we exploited in the attack. So, therefore, they also had relationships like 2f dash, f dash, f dash and 3f dash. Only if you want to go and exploit those differentials, then you have to work behind the 9th round and go there. That means you have to work behind the 9th round key. Okay. So, therefore, you have to understand the relationship between the 9th round key and the 10th round key. Okay, and that can be slightly complicated. And then finally, you would like to reduce the 2 power of 32 candidates, once you have these equations further to 2 power of 8 values. Okay, remember that if you can do this, then this filter also will have a probability of 2 power of minus 24. Okay, that means these 2 power of 32 candidates will get churned, will get filtered and get reduced to 2 power of 8 values, because it is like 2 power of 32 multiplied with another factor of 2 power of minus 24, which will give you on the average around 2 power of 8 values. Okay. So, therefore, in order to understand that, we have to basically look into the equation. So, therefore, here we have been exploiting these equations, and therefore, we have reduced 2 power of 128 key size to 2 power of 32 values. What we now want is we want to work behind and go to these positions, okay, and we want to exploit the relationships here among these key bytes, okay, and reduce them further. So, in order to do that, let us try to derive or just redraw this picture and try to see how the equations work. So, in particular, what I am trying to say is that imagine that this is the fault that you had already like induced, and remember that this fault essentially suppose has a value of p. So I do not really bother about what is the value of the fault can take any random value. And then you have the mixed columns. So let me write this as the mixed columns, just okay. So mixed columns, and then because of the mixed columns you have the differential essentially as follows. So therefore let us just write the differentials here. So differentials are 2p, p, p and 3p, okay. And then you have the XOR of the 9th round key. So this is your K9 which comes into play, and then you have got the sub byte. So I am just writing them as SB and shift row. Remember the 9th round has shift rows, okay. So you have the shift rows here, and then you have because of that, right, these particular bytes gets spread out, okay, because of the shift row. So therefore how does it get spread out? We know that the shift rows does like the left shift. For example, in the first row there is no shift, okay. In the second row this gets shifted like this, then it gets shifted here, and then this gets shifted here. So you have got the values like p1, p2, and this value is like suppose or maybe just write it as p0, and let us write it as p1, this is p2 and this is p3, okay. So these are the 4 bytes that you have, or 4 differential bytes that you have, and then you follow this up by a mixed columns. Because of the mixed columns we have seen that you get those nice relationships that we have just previously seen. So I am just not elaborating them, but just the fact that after this you have got again okay. So here this was actually the 8th round key, okay, because this is in the 8th round. So this fault has been induced at the input of the 8th round, and then what you do is because of here you get these relationships, and then you XOR this with the 9th round key, which is say K9, okay. And after this you have got again a layer of 2 operations, which is the sub bytes and the shift rows, okay. And finally you do an XOR with the 10th round key, which is K10, to give your corresponding cipher. So this is your cipher text. So let us denote it as C10. This is how your differential works, okay. So now if you observe that we basically have exploited, we have targeted these differentials. This has already been targeted, and therefore you have got reduction. Now we want to target these differentials. So the question is, how do I exploit these differentials, okay. So in order to work out that, right, we will basically, right, we see that if you want to work out that, then we basically need to work behind, okay. So remember that in this particular step, right, I mean when you are working behind, you have basically exploited these differentials here, but you work behind and you want to go to these values p0, p1, p2, p3, okay. For this you have to work behind this mixed column. So there is a mixed column which has taken place here, okay. So that means if you want to work behind the mixed column, you have to see the inverse mixed column matrix, okay. So what is the inverse mixed column matrix? So the inverse mixed column matrix is shown here as 14, 11, 13 and 9. So you just can go back and check. So it is 14, 11, 13 and 9. It's a circular shift, 14, 11, 13 and 9, and likewise 14, 11, 13 and 9. So this is your inverse mixed column matrix, okay. So now you observe that if I want to get this particular differential, if I want to get this position or this differential, then I have to take this row of the inverse mixed column matrix, and I have to multiply with this differential here, or this column here, okay. So therefore, right, if you just write down the columns in this way, so this is your the output of the this is the point where you are getting the output of the 9th round cipher, okay. So the 9th round cipher you can write as, so let us just write it down, Z00, 01, 02, C03, then you have got C10, C11, C12, C13, C20, C21, C22, C23, C30, C31, C32 and C33. This is your 9th round cipher. So if you want to come to this location, right, you are basically multiplying this with this column, Okay, so you are multiplying for both the correct value and for the faulty ciphertext, faulty operation, and then you are taking XOR to get the value of this P0 differential. Okay. Likewise, right, if you want for this P1, you have to multiply, like suitably this row with this column. Okay. So likewise, right, you have to basically kind of multiply for the respective columns. Okay. So therefore, right, I mean, right, if you want to do that, then you need to, and if you do that, right, then these are the equations that you get, and let us, like quickly write down those equations. So in particular, right, I mean, you will get the equations as, say, so let me just first of all, so with this, right, we can work out these equations, and so the equations, right, which you will get is, say, 2p, so because, like this is 2p, this pp, this p, and this is 3p, but you get that when you work behind. Okay, so remember, when you get to this differential, after that you can work behind, because you have to just already, right, I have taken care of the shift rows, but when you are working behind, you have to work behind the inverse S box, because there is an S box here. Okay, so you have to work behind this, and that is denoted as S inverse, and the K8 doesn't create a problem because it is a differential. So therefore, if I take the differential, then the effect of K8 gets cancelled out. Okay, so the K8 round doesn't create a problem. So therefore, right, if you work behind, then you get S inverse, and since you are working behind, and I am saying that you have to take the effect of this 14, 11, 13 and 9, so you can write this pretty much as 14 multiplied with C009 XORed with K009. So again, remember that when I am writing K009 means I am considering the 9th round key, and the 9th round key, or the 9th round key, is essentially nothing but K00, K01, K02, K03, and exactly in the same way K10, K11, K12, K13, K20, K21, K22, K23, K30, K31, K32 and K33. Okay, this is your 9th round key. Okay, and this essentially, right, we will see how this 9th round propagates to become the 10th round key. Okay, but right now I am assuming that I am just considering the 9th round cipher and the corresponding 9th round key, and therefore I can XOR them and come to this position. Okay, so therefore, right, I just take and I take 14, 11 and I apply on this. So therefore, this like if you just continue like this, so you get 11 C109. Okay, and that is XORed with K109. Okay, and that is XORed with 13 C209 XORed with K209 XORed with 9 times C309 XORed with K309. Okay, so here you see that we have considered C00, C10, C20 and C30. So pretty much like this column we have multiplied with this row, okay, of the inverse mixed column matrix, and this is for the correct operation, right? These are all for the correct operation. If I want to get the differential, then I have to XOR this with the faulty case. Okay, and the faulty case essentially can be denoted as exactly same. The only thing that we will do is we will write C00 star 9 to indicate that this is the faulty cipher. Okay, so you get K009 XORed with 11 multiplied with C109, but again there is a star, XORed with K109 XORed with XORed with 13 C20 star 9 XORed with K209 XORed with 9 times C309 XORed with K309. Okay. So this is your, at this point you have come to 2p. So you have come to, basically you have got this differential, and from this differential you have so basically you have to come this location, taken the AC inverse, and you have got this differential now. You have come to 2p. Okay, here. But remember, all these key equations have now involved with K009, and these are the 9th round key which I have to kind of express using the 10th round key. Okay. So for this, right, we will just take a look into how the key scheduling works. Okay, and if you see the key scheduling of AES is very simple. So what you do is you just consider them column by column. For example, I consider this column and I consider this column. Okay, and then I basically I do an operation on this column. So this column is essentially like rotate. There is an operation which is called as roteward, and then that is followed by an S box operation. So that means what happens is this K13 goes at the top, this K13 comes at the top, then we have got K23, then we have got K33, and then this K03 comes in, okay, and then we apply an S box operation on them. So this is essentially called often as subword, okay, and then there is a round constant. So in this case the round constant is, say, the 10th round constant is denoted as H10, and you get the final, you get this particular operation. Okay, so this is your this is your first round of the 10th round key. Okay, and then you basically what you do is, once you have got that, you XOR this with the first round. So you basically the first column. So you basically XOR this with K00, okay, and you XOR this with the second value you XOR with K10, then you XOR this with K20, and then you XOR this with K30, okay, and that gives you the first column of your 10th round key. Okay, so this is your first column of 10th round key. For the second column, what you do is, again you take this column, and now so you basically take this column and you XOR it with with something four steps behind, and so you XOR it with this column. Okay, and then you get this column. Okay, and then for the third column of the 10th round key, you basically XOR with the previous column with this column. Okay, and for the final column, you basically XOR it with this column, you XOR the last column of the 9th round key. So that means if you now want, suppose I give you the 10th round key, because remember that you have reduced the key size of key space of AES to some possible values. So suppose you know the 10th round key. So if you want to express the 9th round key, that means you have to just take an XOR of these two successive columns. So if you take an XOR of these two successive columns, you get this column. Okay. Likewise, if you take an XOR or exclusive or these two columns, I mean, if you take an XOR of these two columns, you get the previous column. If you take an XOR of these two columns, you again get this column. So you basically can express the 3 columns of the 9th round key just by XORing successive columns of the 10th round key. Only for the the first column of the 9th round key, you have to just do a little bit of maneuvering to see that there is a cyclic rotation that we have done. Okay, and that for that you have to see like the values of K13, K23, and K33 and K03 of the 9th round key. But remember that like K13, K23, and K33 and K03 are something that you have already observed, or you have already got in the you have already obtained them. You have basically already obtained them and expressed them using the 10th round key. So therefore, if you summarize this entire story, then you can write the corresponding 9th round key in this way. So you can write this as K0010 XORed with S times K13010 XORed with K1210 XORed with H10, and then the second one is K1010 XORed with S times K2310 XORed with K2210 K2010 XORed with S times as K3310 XORed with K3210, and then you have got K3010 XORed with S times K0310 XORed with K0210. Okay, so this is the first column of the 9th round key. But for the others, right, it is very straightforward, because you just do this K01 XORed K0110 XORed with K0010, just basically XORing the successive columns, K1110 XORed with K1010, and then K2110 XORed with K2010, K3110 XORed with K3010, okay, and then K 0 2 10 XORed with K 0 1 10, then K 1 2 10 XORed with K 1 1 10, K 2 1 10, and then K 3 2 10 XORed with K 3 1 10, and then the final column is again in a similar fashion K 0 3 10 XORed with K 0 2 10, and then you have got for the second row which you are just doing is K 1 3 10 XORed with K 1 2 10, and then K 2 3 10 XORed with K 2 2 10, and then you have got K 3 3 10 XORed with K 3 2 10. Okay. So this is your final 9th round key expressed using the 10th round key bytes. So now let us I just write one equation that similarly you can derive, or we can write the other equations. For example, we have already seen that 2p0, or like we have seen that 2p, rather let us write 2p is equal to S inverse of, so like if you just go back for example and just see the previous thing. So in the previous case, right, we have already expressed 2p, but now what I will do is I will like express the C09 in terms of the final round cipher, and I will also express the K09 in terms of the final round key, that is the 10th round key. Okay, so I will kind of write both of these things in and similarly for the other terms also, okay, and complete this equation. So if you do this, right, then let's see how we can do that. So therefore, right, you will basically get this, that is S inverse of, remember, like we are 14 multiplied with S inverse of K00 10, because this is the final round key, XORed with C00, okay, XORed with the 9th round key. Okay, so the 9th round key, as you can see, is here. Okay, so it's written here as or expressed using the 10th round values. So if you just plug in over there, you get K00 10 XORed with S times K13 10 XORed with K12 10, okay, and XORed with H10. Okay, so that gives you essentially this part. And then again similarly, right, you have got 11, and 11 multiplied with S inverse of K13 10 XORed with C13 XORed with the corresponding 9th round value, which is nothing but K10 9th round key expressed in 10th round, expressed using 10th round key, which is S times. So this is essentially this key, that is S multiplied with K23 10 XORed with K22 10, okay, and this XORed with similarly, right, with 13 times S inverse of K22 10 XORed with C22 XORed with K20 10 XORed with S times K33 10 XORed with K32 10, and that is nothing but you can see here is essentially this part of the key, XORed with 14 11 13, and then finally now 9. So you have got S inverse of K 31 10 XORed with C31 XORed with K30 10, again this is this part of the key, K30 10 XORed with S of K03 10 XORed with K02 10, okay, and so therefore, right, I mean this is essentially like one part, and you have to essentially do the same stuff with like I am not writing this part, but only that this part is for the faulty cipher. So therefore you have to just replace these equations with the star variants of them, okay. So therefore, right, therefore this shows that you can express 2p in terms of the 9th round key, okay. So you can continue this in a similar fashion, Basically, as we have seen the dependencies, like we have seen like how to write one of the equations to get to the point of 2p0. Okay. So, we can basically continue in this way, and basically just rather than you can elaborate the equations in a similar fashion, but what is important to note is the number of key bits which essentially are responsible for calculating the values of these differentials 2p0, p0, p0 and 3p0. So, therefore, right, I will just write for the remaining 3 bytes what are the key bytes which are involved. For example, for p0 we have got k0 310, k0 210, k1 310 and k1 210, okay, and k2 110, k2 310, k2 210. So, you have got k03, k02, k13, k12, k21, k23 and k22, followed by k3010, k3310 and k3210. Okay. So, like this, right, you, for the other p0 differential you will have k0210, k0110, k1110, k1210, k1110, k2010, k2210, k2110, okay, and then k3310 and k3210 followed by k3110. Okay. Again, for the remaining differential which is 3p0, you have got the 3p0 depending on k0110, k0010, k1010, k1110, k1010 has already been taken care of. So, you have got k2310, k2110, k2010, okay, and then finally k3210 and k3110. Okay. You also have k3010. So, now if you observe the interestingly, so one possibility is that you know that there are 4 equations. Okay. So, 4 differential equations. So, we have already seen one of the differentials in the previous, for example, this was one of the differentials. So, therefore, right, if I just randomly like take my keys and I substitute them, then I get a value of 2p. So, I can take them and I can like pretty much reduce it by the other 3 equations, and therefore, right, I mean if I do that, then there will be like 2 power of 32, like for every 2 power of 32 keys I have to kind of substitute in these equations and I have to solve them. Okay. So, I can do slightly better by observing an important property of the key schedule here. That means, if you observe the number of key bytes which are responsible, for example, if I just quickly write down this k0001, k02, k03, k10, k11, k12, k13, k20, k21, k22, k23 and k30 and k31, k32 and k33. So, this is your 10th round suppose key bytes. You will see that these 2 equations, there is no key byte which actually depends upon these 2 key bytes. It does not depend upon k00 and it does not depend upon k10. Okay. So, that implies that you can actually do an interesting, like you can utilize this in an interesting manner, and like that can be like exploited to reduce the time complexity of the attack. So, with this background, let us just like get back and see that how you can reduce the, we have already reduced from 2 power of 120 to 2 power of 32. So, now what you can use the equations that we have just now seen, and they, like there are 4 further differential equations, and therefore, right, you know that for those further differential equations which you can summarize in this format. So, this is the compact way of writing them. You know that the probability of a random key to satisfy this is 2 power of minus 24, and you have got 2 power of 32 keys from the first phase. So, on average you will be 2 power of 8 keys will survive. But now, if you take all the 2 power of 32 keys and if you plug into them, then your time complexity is still 2 power of 32. Okay. So, now we will exploit just now the fact that we have seen and reduce like the time complexity of the attack. So, therefore, if you do this right, then definitely you can reduce the key size, but how can you improve upon the time complexity? So therefore, right, what we do now is we observe as we have. So this is essentially which we can trivially observe here is that you can reduce the key size to 2 power of 8 values, but the time complexity is 2 power of 32. So what you can now do is, based upon the previous observation, that it does not depend upon 2 key bytes. So this is another like naming convention that we have. So there are different, the way I like showed the key bytes essentially was by the rows and the columns. So typically another way of like, or another naming convention is in this way, like K0, K1, K2, K3, K4, K5, K6, K7, K8, K9, K10, K11 and so on till K15. Okay. So this is essentially in a like you are basically doing the across the columns. Okay. So here we have seen that it equations 2 and 3 does not depend upon these 2 key bytes. Remember, this was my K00 and K10 in the previous nomenclature. That is, it does not depend upon K0 and K1. Okay. So therefore, what you can do is you can do this attack in a nicely in a divide and conquer manner. So what you can do is elaborated here. For example, what you can do now is you can try to accelerate this process by breaking up. So this is the initial key quartets. For example, like suppose this is your first and fourth key quartet. So remember that like you have got A1, B1, C1, D1. These are all your key quartets. Okay, and each of them have got size 2 power of 8. Okay, because you had got for every key quartet there are 2 power of 8 values, 2 power of 8, 2 power of 8, 2 power of 8, 2 power of 8. That's why we got 2 power of 32. But now what you can do is that one of these key quartets you can actually break it up into 2 parts. Okay, so one part is shown here as like L1 and the other part is L2. Okay, so note that there are some interesting observations here. If you see the contents of this table, we have written like A1, B1, C1, D1, A2, B1, C1, D1. That means the way the key quartets will occur. Okay, so you will find that you will get solutions like A1. So suppose like you have for three key bytes, if you get B1, C1, D1, you will find that there are 2 values of A1, A2 which will be along with this. Okay, so I'm not explaining why this happens, but I'd rather leave it to an exercise with a small hint. That is like the form of these equations is of this form, right? S inverse of x is equal to S inverse of x XOR alpha is equal to a beta. So therefore, if I fix alpha and beta, and suppose like you get a solution at x equal to x1, this implies that you also have another solution at x equal to x1 XOR of alpha. Okay, so therefore there are 2 solutions for every beta that you get. Okay, and that is why you get the solutions in pairs. So therefore now that's why you can split this into 2 parts, and you can essentially like you can write those 2 key value, those 2 values of K0 for example, and write A1, A2, and in the other table, right, you have got the remaining values like B1, C1 and D1. Okay, so likewise you can split up this key quartet also into 2 parts, L3 and L4. So now what you can do is remember that we know that equation 2 and 3 does not depend upon K0 and K1. So you can kind of leave that, and the other part of the key, right, I mean other part of the key quartet, that is L2, the size of this, right, is 2 power of 7, because totally it was 2 power of 8 which we have broken up into 2 parts. So here there are 2 values, and here there are remaining 2 power of 7 values. Okay, so therefore the maximum size of this list L2 becomes 2 power of 7. Likewise the maximum size of like the of this list L4 is also 2 power of 7. So therefore what I do is I take these 2 power of 7, these 2 power of 7, and for the other key quartets, so the second and the third key quartets where there are 2 power of 8 and 2 power of 8 values. So totally if I multiply, I get 7 plus 7 14 plus 16. Okay, and I take them and I reduce them by test 1, which is my equation 2 and 3. Okay, and then right I bring this K0 and K1 and I reduce them by test 2. Remember, in test 2 I can actually parallelize this process. So you can basically pretty much do this test in parallel. Okay, and like you can further reduce it. So basically, right, what I am trying to say here is summarized also in the like in the next discussion here. For example, what you can observe here is that L1 contains K0, L2 contains K13, K10 and K7, that is the remaining 3 bytes. L3 contains K1, L4 contains K4, K14 and K11. Okay. So the second and the third key quartets are represented by 2 lists L5 and L6, each of dimension 2 power of 8. So therefore now if you look at equation 2 and 3, you have got these lists, and therefore the total dimension is 2 power of 30, and therefore if you now use equations 2 and 3, then you can reduce it to 2 power of 22 candidates. Okay. Now these 2 power of 22 candidates you combine with the other 4 values of k0 and k1. So therefore the size of this, right, will increase to 2 power of 22 multiplied with 2 power of 2, that is 2 power of 24. And then you use equations 1 and 4 to reduce this 2 power of 24 to the final 2 power of 8 values. So remember, if you do in this way, then your size never exceeds 2 power of 30. Your size, right, is always 2 power of 30, and therefore the time complexity of the attack does not shoot beyond 2 power of 30. Okay. So there is an improvement over the previous 2 power of over the previous attack where the time complexity was 2 power of 32. Okay. So therefore, right, you have basically been able to do the attack in a technique which is 4 times faster. Okay. So to summarize, DFA on AES can be done with a single fault. A single byte fault at the input of AES 128 can reduce the key size to only around 256 guesses, and in the optimized version one can do the attack with a time complexity of 2 power of 30, which is like a 4 times improvement over a straightforward approach, okay, using the property of the AES key schedule. So here are some references that we have used in the discussion, and of course, like, you can refer to the original textbook for more details. So with this, I would like to say thank you.